In this lesson, we're going to apply the remainder theorem and the factor theorem. So the remainder theorem tells us that if we're taking a polynomial and dividing it by x minus c, then the remainder is the same as when we plug in f of c. So here's what we mean by that. Let's take a look at our polynomial f of x, and I want to evaluate f of 1, which means every time I see an x, I replace it with a 1. And that gives me 5 times 1 to the 7th, which is 5, minus 3 times 1 to the 5th, which is minus 3, 2 times 1 squared, which is 2, and then minus 1. That gives me 5 minus 3, which is 2, plus 2, which is 4, minus 1, which is 3. So what that tells me is that f of 1 is 3. Now, using the remainder theorem, it should be that when I'm finished, I have a remainder of 3. And so f of 1 means that the binomial that I've divided by is x minus 1. So let's take a look at what it would look like if I divided by x minus 1. That would be 5x to the 7th, 0x to the 6th, negative 3x to the 5th, 0x to the 4th, 0x to the 3rd, 2x squared, 0x, and minus 1. Now we know how this works. This is synthetic division, which is the easier one. I bring down the 5, and then I multiply. 5 times 1 is 5. 0 plus 5 is 5. 1 times 5 is 5. Negative 3 plus 5 is 2. 2 times 1 is 2. 0 plus 2 is 2. 1 times 2 is 2. 0 plus 2 is 2. 1 times 2 is 2. 2 plus 2 is 4. 1 times 4 is 4. 0 plus 4 is 4. 1 times 4 is 4. Negative 1 plus 4 is 3. Notice my remainder is 3. This was a heck of a lot of work, but notice that my remainder of 3 is exactly the same as what I got when I plugged in f of 1. So that's very helpful for us. So I know that those two values will be the same, so I'm not going to do it this way anymore because it takes way too long. Whereas here, I can just plug in the value, and if I have a graphing calculator, I can actually enter this as a function and then enter f of 1, and it will determine the solution for me, which is nice. So the factor theorem tells us then that if f of c equals 0, which means when I plug in the value I get 0, that means there's no remainder. That means x minus c is a factor of the polynomial. So all of this is going to lead us up to being able to factor polynomials completely, even when they have a degree that is above what we've done in the past. So here's what we're going to do. It says use the factor theorem to show that radical 5 is a 0 of this function, which means if I plug in radical 5, and when I'm finished all the way down at the end when I'm shown all my work, if I get 0, that's going to tell me that radical 5 is a 0 of the function. So let's see if it works. Radical 5 cubed minus 4 times radical 5 squared minus 5 times radical 5 plus 20. Radical 5 cubed would be 5 radical 5. Radical 5 squared would be 5 times minus 4 would be minus 20. Then I have 5 radical 5 plus 20. Notice these two values cancel out to give me 0, and these two values cancel out to give me 0, and so I do end up that f of radical 5 equals 0. So using the factor theorem, that tells me that x minus radical 5 is a factor, and that radical 5 is a 0. So this is a factor, and this is a 0, which is of course what I would get setting this factor equal to 0. Here's one using an imaginary number. So show that 8i is a 0. So we can do this just as we did before. 8i, I'm going to plug that in for f. So 2 times 8i cubed plus 8i squared plus 128 times 8i plus 64. If I cube 8i, I'm going to leave this 2 out here for now. If I cube 8i, I get 512 I to the third, and we'll come back to that. If I square 8i, I get 8 times 8, which is 64, and then I squared. 128 times 8 gives me 1024i plus 64. Now let's remember that I squared is -1. So here I'm going to call this negative 512 with an I left over, because 2 of the i's became -1, but I had an I left over. This is going to be 64 times -1, which is of course -64. And everything else I'm leaving alone for now. 2 times -512 is -1024i. I have this plus -64 or -64 plus 1024i plus 64, and now you can see these two values cancel and these two values cancel, and I get a 0. Now if I wanted, I could also use this 8i to plug it in the synthetic division, and I should end up with a remainder of 0 also. That would be more work in this case, and therefore I'm not going to do it because I'm lazy. So here, same idea. We're going to use the factor theorem to determine if x plus 4 is a factor, and if it is, then what is the 0? So if x plus 4 is a factor, that means I'm plugging in -4. So remember, I'm taking the x plus 4 and setting it equal to 0 to find what value to plug in, and that would of course be -4. So 6 times -4 cubed plus 11 times -4 squared minus 60 times -4 minus 32. That gives me -64 times 6, which is -384. -4 squared is 16 times 11, which is 176. Minus 60 times -4 is plus 240, and then minus 32. Combining those 4 values together, I do get 0. So with a solution of 0, that tells me that x plus 4 is a factor of this polynomial. It also tells me that a 0 is -4, which is of course the value that I plugged in. Try this one on your own and then press play to check your work. So again, instead of doing any of the division, I'm just going to plug in, if I said x minus 6 equal to 0, that gives me +6. That's the value I plug in, so f of 6. So 2 times 6 to the 4th minus 13 times 6 cubed plus 10 times 6 squared minus 25 times 6 plus 6. Again, feel free to use a graphing calculator, enter this original function, and then just say f of 6, and it will pop out the answer for you. So in doing all of my calculations and adding and subtracting those values, I find that it is equal to 0, which means the remainder would be 0, which means that x minus 6 is a factor. The 0 would be +6.